Today, I'm going to continue on induction. So I should probably slow down and discuss things. So in discrete, kind of the huge bulk of the time is spent in one, which is logic and proofs. And then we also spent a lot of time in sets, right? So these are like most of the time. Then the rest of the class is going to be done in kind of short bursts. So we're doing induction, but we're only going to do 5.1 and 5.2, and we're probably going to move on to a different chapter by Friday, I would guess. So induction is going to be this short little week's worth of induction. Then we're going to do like a week and a half's worth of number theory, which is chapters like 4, probably 0.1, 0.2, 0.3 or something. Like we're gonna do some stuff in number theory, but this is also like 1 week or maybe 4 days. Then we're gonna go to chapter 9, which is equivalence relations. 9 point, probably we're only gonna do like 1 or 2 sections here as well. And then we're gonna do combinatorics, which is chapter 6. So the point is that we've spent a lot of time going very slowly through logic and proofs and sets. And now we're going to kind of apply our skills, our knowledge of sets, our knowledge of induction, to kind of examine a couple topics gently and quickly. So we're not going to go super in depth into this stuff. It's just going to be kind of some basic math that we're going to examine through the lens of the tools that we've developed. Probably it would be very good if I sent y'all a list of the actual sections that I'll plan to cover. So I'll do that later today. Any questions on the plan for the rest of the course? Okay, another thing is that I have graded your exams, and I'll talk about them at the end of class today. It's just good to not get distracted while we're teaching. Last chance for questions before we go back to induction. Did I submit the grades? No, I haven't submitted the grades. I'll submit the grades at the end of class. I just want to get a chance to talk about it first, that's all. Okay, so induction. Can someone give me a rough idea of what induction is or what induction does? Hang on, I'm going to close my front door, but you can still either say something or write something. Okay. What is induction? Yep, it's a way to prove statements for all positive integers. A way to prove statements like Pn for all n greater than or equal to 1, or maybe n greater than or equal to b, right? It's not going to be holding for all values of a set. It's going to be holding for all values of a very specific set, namely a subset of the positive integers that has no gaps, right? I kind of, well, that's not exactly true, but there's a lot of structure on this collection of n's, right? Like I have some base case, the lowest one, and then I have a way of getting everything higher than it on the ladder, so to speak. So it's a very special kind of set of positive integers that we're proving things about, statements that are indexed by subsets of the positive integers. So the idea, of course, is have a base case. This kind of gets you started, and then you have an inductive step, which gets you from case K, from say PK to PK plus 1. And so in this fashion, you can climb the ladder of induction, so to speak. So I did one worked out example last time, and what I'm going to do today is mostly do other worked out examples, but maybe kind of slowly so that y'all have some input. Okay? I know it's Monday. It's Monday for me too. Okay, let's do an example. Let's prove that 1 plus 2 squared plus 2 cubed all the way up to 2 to the n, this big sum of powers of 2 is equal to 2 to the n plus 1 minus 1. Okay, my first step before I even start, doing proofy things is, how do I express this as a statement P of n? What is the statement P of n? Or maybe I should do P of k, but there are plenty of ways to prove this, yes, but for now I'm using induction. And it's correct that this could be interpreted as a statement in base 2 arithmetic, sure. So in this case, yeah, Pn is exactly this statement. I could write it as a summation from I is equal to 1 all the way up to n of, sorry, I should not do this. Here I'm going to start my indexing at 0. So this is showing a little bit of flexibility. We don't have to start it at 1. I can choose a different base, like 0 or 7 or something like that. Here I'm going to choose 0 because 1, because everything here looks like 2 to a power, right? 2 to the n. And of course, 1 is 2 to the 0. So this is 2 to the I is equal to 2 to the n plus 1 minus 1, right? So this will produce exactly this statement, this summation, starting from I is equal to 0. Okay, so what is my base case? Yeah, exactly. My base case is going to be P of 0. And for P of 0, I plug in 0 to both sides. So what do I get if I plug in 0 for n on the left-hand side? Well, I get the summation from I is equal to 0 to 0 of 2 to the I, which is of course equal to 2 to the 0, which is equal to 1. And then the right-hand side, so this is the left-hand side. The right-hand side is 2 to the 0 plus 1 minus 1, which is equal to 2 minus 1, which is equal to 1. So once again, the base case of an induction is usually just a calculation. I just calculated when n is equal to 0, One side is 1 and the other side is 1, and they're equal. So this concludes the base case. What is the next step? Right. The next step is the inductive step. And what do we assume for the inductive step? Right. We want to assume P of K and use that to prove P of K plus 1. So the inductive step, what I'm going to write here is we assume that P of K is true. Namely, what does it mean if P of K is true? Well, it means that the summation from I is equal to 0 up to K of 2 to the I is equal to 2 to the K plus 1 minus 1. Right? Is this okay? I'm just here. I know that it was kind of silly or trivial to write down what P of n is, but it's kind of very helpful to have the statement P of n because I'm going to be using that for different Ks and K plus 1s and zeros all over the place. So it's helpful to know, like, you want to be very clear with what you're writing for statement P of K. Okay. So now we want to show P of K plus 1 is true. And so in the 7-step program or whatever for induction, they next recommend that you literally write out P of K, but I kind of disagree with that because you run the risk of assuming P of K plus 1. Sorry, they tell you to write out P of K plus 1. So I'm just going to write out the left-hand side of P of K plus 1. The left-hand side of P of K plus 1 is this. I is equal to 0, so I is equal to 0 up to K plus 1 of 2 to the I. Well, here I want to kind of expand this out. This is equal to 1 plus 2 plus 2 squared plus 2 to the K plus 2 to the K plus 1. Okay. So I've written out the left-hand side of P of K plus 1, and I want to show that it's equal to the right-hand side of P of K plus 1. So what do I do here?
Would we solve for P of K plus 2 to the K plus 1?
Yes, exactly. I recognize this chunk right here as being exactly the left-hand side of P of K. And if P of K is true, then what does this equal?
P of K?
Well, P of K is a statement, but P of K is the statement that this is equal to this. So the left-hand side of P of K is this, and if we assume P of K is true, that means I'm going to be able to replace this with 2 to the K plus 1 minus 1. Yeah. So this is what is called the inductive hypothesis. This is where I use my assumption on P of K to do something with the expression for P of K plus 1. So this is going to be equal to 2 to the K plus 1 minus 1 plus 2 to the K plus 1. Right? This step of swapping this sum for 2 to the K plus 1 minus 1, I'm allowed to do exactly because I assumed P of K is true. And P of K is these two things are equal. Is everyone okay about this swap that I did, this switch? Okay, you have run out of time to protest. So now we just use algebra to simplify the rest of the step. What is 2 to the k plus 1 plus 2 to the k plus 1?
2 to the k plus 2.
Yeah, this is 2 times 2 to the k plus 1 minus 1, which is equal to 2 to the k plus 2 minus 1. Ah, what is this?
P of k plus 1.
Yeah, this is the right-hand side of p of k plus 1. Like off to the side, you shouldn't write this in your proof because you run risks, but p of k plus 1 is the statement that the sum from I is equal to 0 up to k plus 1 of 2 to the I is equal to 2 to the k plus 2 minus 1. And what I did is I took this over here and using the inductive hypothesis and some algebra, I worked out that it was equal to 2 to the k plus 2 minus 1. So thus, or this finishes the inductive step. Thus, the proposition is true by induction. Okay, did I hit every step in the 7-step program? I hope I did, because I just hope so. Any questions about this proof or about some part of this proof? No? Okay, that's all right. I don't mind. I'm not hurt. Oh, I'm sorry. I'm sorry. Okay, let's do a different example. Different example. So now we're going to prove something from calculus, which is very exciting. New example. Calc 2. How many of y'all had Calc 2 as your favorite math class ever? You can raise your hands in the chat. I'm seeing not very many hands. Well, we're going to prove some fun fact from Calc 2. Okay, so recall, I'm going to define a number called a harmonic number. The harmonic numbers, which are hj is equal to 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus ... all the way up to 1 over j. So in particular, h1 is just the number 1, h2 is 3 halves, which is 1 plus 1 half, h3 is whatever 1 plus 1 half plus 1/3 is, which is like 11/12 or something, whatever. h4 is equal to 1 plus 1 half plus 1/3 plus 1/4. And of course, something that's very interesting is the series version of this, the harmonic series, which is the sum 1 plus 1 half plus 1/3 plus 1/4 all the way on to infinity, right? That's a series that is of great importance in Calc 2 when you're trying to examine series and when they converge and whatnot. Okay, so what we're going to prove is that a special harmonic number, namely h to the 2n, is greater than or equal to 1 plus n over 2. Okay. So the first thing that I want to do here is, and this is always a good example when you're doing induction, is to do a couple examples and check that this is a reasonable thing. So I'm going to write out some h to the 2n's. Well, okay. H to the 2 to the 0, which is equal to h1, is equal to just 1. Okay, so let's check. Is 1 greater than or equal to 1 plus 0 over 2? Yeah, they're equal. H2 to the 1, which is equal to H2, is equal to 1 plus 1/2. And my question is 1 plus 1/2 greater than or equal to 1 plus 1/2? Oh yeah, definitely. Let's do a couple more examples. H2 squared, which is equal to h to the 4th, not h to the 4th, h sub 4, is equal to 1 plus 1/2 plus 1/3 plus 1/4. Here's the first kind of non-trivial example. The question is this number 1 plus 1/2 plus 1/3 plus 1/4, is this greater than 1 plus 2 over 2? Is this greater than 1 plus 2 over 2? Question mark. Why do you say yes so confidently, both of you? Math is an excellent answer. Yes, I would say exactly that, but with a slight change. I would say 1/3 plus 1/4 is greater than 1/2, right? And you can check that. 1/3 plus 1/4 is going to be, if we find a common basis, it's going to be what, 4 over 12 plus 3 over 12, and when you add them up, you get 7 over 12, which is greater than 1/2. Right. So I'm looking at this kind of tail right here, and I'm saying, look, this tail is greater than 1/2. And all that I wanted is 1 plus 1/2 plus 1/2, right? That's what this number is, 1 plus 1/2 plus another 1/2. Let's do one more example. Now my work is getting very messy. You'll have to forgive me. H8, h2 to the cube is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And now my question is this greater than or equal to 1 plus 3/2? And what do y'all say? You can plug this into Wolfram Alpha and say, yes, it's true because of math, which is, of course, a correct and good example. Or you can do it in your head. I can't. But here's the point. This is greater than or equal to 1 plus 3/2 for the following reason. This is 1. This is 1/2. We already saw that 1/3 plus 1/4 is greater than 1/2. And now I claim that 1/5 plus 1/6 plus 1/7 plus 1/8, you know what this is greater than? This is greater than 4 times 1/8, right? Because I'm adding up things that are bigger than 1/8. And 4 times 1/8 is equal to 1/2. So this thing is also bigger than 1/2, right? So I'm going through this list. This is 1, this is 1/2, this is bigger than 1/2, this is bigger than 1/2. I can see that I can break up the parts of this harmonic series into chunks such that each chunk, or the first chunk is 1, the second chunk is 1/2, the next chunk is going to be bigger than 1/2, the next chunk of 4 is going to be bigger than 1/2. If I did another step, I'd add on another 8 terms all the way out to 1/16. But then this whole chunk would also be bigger than 1/2 because it'd be bigger than 8 times 1/16. Does anyone have any questions about what I'm kind of sketching out here? Thank you. I didn't come up with it, but you know, thanks. Any questions here? So probably when you were in Calc 2, someone should have told you that the harmonic series diverges. And when they told you that the harmonic series diverges, remember that a series diverges if its sequence of partial sums diverges. I hope y'all remember that. And what I'm showing you here is that the sequence of partial sums, if I only look at the partial sums given by h to the 2n's, they're always bigger than some number of 1 plus 1/2, where there are n of the 1/2. So essentially, when I prove this statement, this will be, or a quick corollary of this will be that the harmonic series diverges, which is something that you used all the time in Calc 2, maybe without proving it rigorously. And induction is how we prove this rigorously. Any questions about what I'm about to do? Okay. So let's actually prove it. Let's do, so proof by induction. What are some convenient base cases that I could pick? P of 0 is a very reasonable base case here. P of 0 is going to be the statement that h of 1, which is equal to 1, is greater than or equal to 1 plus 0. So this is h of 2 to the 0 is equal to h1 is equal to 1, which is greater than or equal to 1 plus 0 over 2. This is true, since 1 is indeed greater than or equal to 1. Another perfectly reasonable base case to do is P of 1, right? So here I'm saying h2 to the 1 is equal to h2, and h2 is equal to 1 plus 1/2. And this is indeed greater than or equal to 1 plus 1 over 2. In fact, they're equal. So P of 1 is true as well. P of 0, P of 1 are true. Now for induction, or for standard induction, you only need one base case, but it's not a bad idea to have a couple base cases. P of 0 is true, P of 1 is true, cool. And actually, in the next chapter, we'll do strong induction, which possibly requires several base cases, so to speak. Kind of. Okay, so what's the next step? The next step is the inductive step. Oh, I should have said base case, and underlined it. Inductive step. We assume that h 2 to the k is greater than or equal to 1 plus k over 2. Is this indeed P of k? I think this is P of k. Now we examine h of 2 to the k plus 1, which is equal to 1 plus 1/2 plus 1/3, all the way out to plus 1 over 2 to the k plus 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 2 plus all the way to 1 over 2 to the k plus 1. Right? I've just written out the left-hand side of p to the k plus 1, which is h 2 to the k plus 1. Okay, what do I recognize here? I recognize pk here, or really hk, h 2 to the k. This is the previous power of 2 harmonic number, right? The sum from 1 all the way up to 1 over 2 to the k. Excellent first thing to recognize. Second thing that I'm going to recognize is how many terms are here. How many terms are being summed up here? Let's go kind of back up here and notice that when I'm trying to compare, when I'm looking at h of 8, then h of 4 is the first 4, and what remains, the new tail, is of size 4. So whenever I do this cut, I'm taking half of the terms with the first half, and this is 2 to the k. So how many terms are going to be in the second half? I claim it's 2 to the k, right? Here, another way to think about it is if I'm adding up from 2 to the k plus 1, so I have one term here, 2, 3, 4. How many times do I need to add things up until I get 2 to the k plus 1? So 2 to the k plus 1 is equal to 2 times 2 to the k. So in between there, I have 2 to the k worth of terms to go from 2 to the k all the way up to 2 to the k plus 1. 2 to the k terms. Are we okay with this? I think if you do the h to the 16 example, you'll see very clearly why I have 2 to the k terms. Actually, why don't I just write out h to the 16? You know, show and not tell. h16, which is equal to h 2 to the 4, this is going to be equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9. Look at what I'm doing for you. Plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. Let this be proof that I care deeply about my class and my students. Okay, so what I've got here is h to the 2 to the h sub 8, namely I've got the first 8 terms here. And then when I'm going all the way out to 16, I'm adding up all the terms. If I just look at the bottom, it's the difference between 8 and 16. That's just going to be another 8, right? This is also 2 to the 3rd terms. And you can believe that I would have the same thing if I looked at h to the 32, which is the next power up. However, I don't care about my class that much to write out 32 terms. I would in office hours. Okay. So are we happy about this this way of understanding h to the 2k plus 1? Yeah, in office hours, we can do 64 terms. Okay, great. I've wasted enough time, is what someone is saying. Okay, so by the inductive assumption, by the inductive hypothesis, h to the 2k plus 1, well, what do I know about this first term, this first half of h to the 2k plus 1? What do I get by the inductive hypothesis? What does my inductive hypothesis say? Yes, my inductive hypothesis says h 2 to the k is greater than or equal to 1 plus k over 2. So if I've got h 2 to the k here, my inductive hypothesis is that this term is greater than 1 plus k over 2. So this whole thing is greater than or equal to 1 plus k over 2 plus this junk. 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 1. Okay, and now what am I going to do with this junk? Well, I claim, let me write one more term, 1 over 2 to the k plus 2, 2 to the k plus 2, not 2 to the k plus 2. I claim that each of these terms is greater than or equal to 1 over 2 to the k plus 1, right? In my example, I'm essentially just claiming that 1/9 is greater than 1/16, and 1/10 is greater than 1/16, and 1/11 is greater than 1/16, right? All of these numbers are greater than or equal to the smallest one. So this whole thing is greater than or equal to 1 plus k over 2 plus, I'm just going to replace all these by 1 over 2 to the k plus 1 plus 1 over 2 to the k plus 1 all the way out to plus 1 over 2 to the k plus 1, right? If I replace all these numbers by 1/16, the number has gotten smaller, and I'm doing the exact same thing here for k. How many terms are here? Well, there are 2 to the k terms, right? We already counted how many terms are appearing here. 2 to the k terms. So this whole thing is equal to 2 to the k times 1 over 2 to the k plus 1, right? That's what it means if I have 2 to the k terms and each of them is 1 over 2 to the k plus 1. What is 2 to the k times 1 over 2 to the k plus 1? Yeah, that's 1/2. So this whole thing is equal to 1 plus k over 2 plus 1/2, which is equal to 1 plus k plus 1 over 2. So we have finally proven p of k plus 1, namely h of 2k plus 1 is greater than or equal to 1 plus k plus 1 over 2. Thus, the inductive step is complete. So h2 to the n is greater than or equal to 1 plus n over 2 by induction. Corollary, the harmonic series one plus 1/2 plus 1/3 plus ... diverges. Beautiful, absolutely beautiful, lovely. Questions here? That's true, but since I am the instructor of this class, it is useful for your interpretations of mathematical beauty to align with my interpretations of mathematical beauty, at least for the duration of the course. Yeah, I mean, you shouldn't be so worried, right? Like, this is something that you can practice, and this is something that you will get practice on with the exercises, and I think that this will be more reasonable. It is true that there is a mathematical leap that is required, which is to kind of break it up into the first half and the second half and examine, you know, that the second half is bigger than something. I think that with some practice on the induction problems, I think that you'll find the majority of the problems a little more reasonable than this. Any further questions? So you should definitely expect some induction, but I would say you should expect an induction problem that's similar to what you have on your homework, and this is maybe the upper limit of what could possibly be asked. Okay, time to talk about the exam. So the exam in general was kind of rough. But that is because I graded it pretty harshly, I want to say. I graded it pretty with an eye towards rigor. So here is my proposal. My proposal is that you can win back half the points you missed by simply turning in a perfect copy of midterm 2 before the final. So this, in other words, if you got 50 out of 100, would become a 75 out of 100. And a 60 out of 100 would become an 80 out of 100. Yeah, see, this is better than dropping it. So, you know, and another thing too is I'm willing to literally tell you what the solutions are on this exam. I want to, before the final, so you've got like a month. So what I want to do is I want y'all to come talk with me, make an appointment with me. Let's talk by let's talk about this midterm in office hours. Let's talk about this midterm in like a different session from the office hours. I want to just discuss all the parts of this. And so the point here is not to make y'all like suffer due to grades. The point is for you to see kind of what a rigorous proof looks like and then write up a rigorous proof. And you have time to do this. So don't stress too much about this. Before class ends, I want to go over some things that were often missed, frequently missed problems. One is that if m1 and m2 are irrational numbers, then m1 plus m2 can be rational. A lot of people missed this. A lot of people saw two irrational numbers and they said, well, their sum obviously has to be irrational. But an extremely quick counterexample is that square root of 2 plus negative square root of 2 is equal to 0. And this is rational. And this is obviously, each of these are irrational. So the proof strategy for the one where you're proving that a certain sum was irrational cannot just go by saying, I have two irrational numbers, therefore their sum is irrational, because that's simply not true. The correct way to go about this problem, so I'll just sketch it right now. I'm happy to go in much more detail in office hours, but the correct way to go about this problem is you assume square root of 2 plus square root of 5 is rational. Then you get square root of 2 plus square root of 5 is equal to p over q. Just as when we were proving square root of 2 is irrational, and then you square both sides to get square root of 2 squared plus 2 square root of 2 square root of 5 plus square root of 5 squared is equal to p squared over q squared. And then you get 2 plus 5 plus 2 square root of 10 is equal to p squared over q squared. And here is where you use the hint that the square root of a non-square is irrational. You're trying to use the fact that square root of 10 is an irrational number. And then from here, you'll get a contradiction. So that's one place that many people didn't provide a correct proof. Another common mistake was the rigorous definition of a function as a relation. So a function f from a to b is a relation R, which is a subset of A cross B, such that for all A in A, there exists a unique tuple A comma B inside the relation. If you gave me a different, the test to use to see whether your definition of a function holds up or not is the next problem, because such a definition has to be able to handle when one of these sets is the empty set. So the next part of the problem was how many functions from the empty set to A, this is the answer is 1. There's one function from the empty set to A. It's called the empty function. One function, the empty set, which is the subset of the empty set cross A, which is equal to the empty set. There is one subset of the empty set, namely the empty set. How many functions from A to the empty set? The set of functions from A to the empty set doesn't exist, or it's the empty set. The cardinality of the empty set is 0. There are no functions from A to the empty set. So the cardinality of the empty set is what we're after. and the cardinality of the empty set is equal to 0. Here are some, these weren't worth too many points, but they were kind of commonly missed. Yeah, so basically what I want to let you know is, oh, probably I'm over time. Yeah, so I'll release the grades kind of right away. Set up a meeting, talk with me. I'll discuss every single proof in very clear detail with you. And then all that I ask for your grade to be boosted in this fashion, where you regain half of your missed points, is that you submit a perfect copy of the exam before the final. And you can like discuss with me and say, is this perfect? Is this proof correct? Is this proof correct? And as long as it's what we discuss in office hours or something, then you'll get a bunch of points back. Sounds okay? I hope so. Don't stress too much. Let's chat about this. And everyone have a nice Monday. Also, I have office hours today at 10:30. Janae, Luke, and Rohan, do any of you have questions? I should stop recording. Cool. All right, Rohan?